Hello everyone, October 7th. Alright, let's do this. I was supposed to do this yesterday, but wasn't able to. So today actually gonna be two. So I'm gonna do one here right now, and I'm gonna do another one later. Alright, you're given three integers, n, m, x. Consider the following algorithm to find the maximum elements of an array of positive integers. Wait, hold on. Build an array where you can find the maximum in exactly k comparisons. Wait, what? 3n, m, and k. Consider the following algorithm to find the maximum element of an array of positive integers. Search cost. Okay, you should build the array which has the following properties. The array has exactly n integers, where every one is in between 1 and m. After applying the method mentioned algorithm to array, the value search cost is equal to k. What the hell is this? Return the number of ways to build the array. Number of ways to build the array under the mentioned conditions. What the hell? Alright, so basically this is saying the search cost is each time if you find something that's, if the current one is larger than the maximum, then you have to, basically if you lay out your array from small to large, and every time you have you accumulate the search cost. Alright, so search cost is whenever something is bigger than the previous, which means if you want a search cost is 1, you have to put the largest at the front, right? So basically, if you have an array with search cost, you have to put, if let's do this, right, search cost is, if search cost is 3, right, if k is equal to 3, then you have to have like this. Then we have one hit, 2 hit, 3. So the search cost kind of give you an idea of where these key elements are going to be, right? And everybody else, like anything in front of this, shall be smaller than that. This one shall be smaller, and this shall be smaller than everybody. No, just then this. Hold on. So we have the anchors. We call them anchors, right? So anchor 1. Anchor 2, so we have something, anchor 3, and then we can go all the way to anchor k. All right, so that's k anchors, and they has to be like this. Furthermore, anything in between, and we can call these, let's call them b. Okay, so will be b1 1, b1 2, all the way, no, b1 1, b1 something. And these has to be smaller than a1. No. A1 is the first one, my bad. A1, because you have to have one cost to start with, because it's positive integer. The return value is a positive integer. So array is positive integer, which mean, and then start with -1, which means this is the first one. This is the first element in the array, right? So this is the first one, and everybody here needs to be smaller than this, and we don't really care about the order. As long as they're smaller than a1, we're happy, right? Okay, so based on the cost, kind of know, and we have the total number, okay, and I think the total number doesn't matter too much, but the m, because everybody has a smaller than m. So when k equal to 1, which means in the sorted one, we only need to have 1, right? And then it has to be smaller than 3, and the total is 2. So it's gonna be a1 something, right? A1 something. and this has to be smaller than 1. This has to be smaller than 1. So now we ask is when we hit A1, we can be 1. If A1 is 1, then it can only be 1. It's 2, we can do 1, we can do 2. If it's 3, we can do 1, 2, 3. So in total is 6. Makes sense. Second, n is 5. So we have I have 5 slots, right? 1, 2, 3, 4. K equal to 3. So we need 3 things. So we need 3 spots. Okay? 3 spots. And basically just want to know what those 3 spots are, and m equal to 2. Okay, so k, the smallest the k is going to be just 1, 2, 3 all the way to 3, right? That's the smallest. And now you say m is smaller equal to 2, so that's not possible, right? Because the smallest you can get is 3. Smallest you can get is 3. But now you say m equal to 2, which means it has to be smaller than 2. So m determines, all right? M determines what number you can get, all right? M determines what number you can get, and this is just all ones. So m determines what values you can get. So give you an m, right? Give you an m, you have 1, 2, 3 all the way to m. Okay, so if m is smaller than k, it's not possible. So that could be like the very first thing we can put in there. We just not really starting doing it. We just start to just probe around the problem. So if m is smaller than k, right, that is an impossibility. So we just return 0. Right? Straight and simple. It's not possible, right? It's not possible. Now m is larger than k, okay? So now we say m is larger or equal to k. Or we can say, what if m is equal to k? Well, if m is equal to k, that's only 1, right? That's only one possibility, because m tells you 1, 2, 3 to m. K, this the sorted, right? The sorted value that you can hit is also 1, 2, because you cannot. You have to have at least k. Right? You have to have at least k values in sorted order. And if you only k is equal to m, then there's only one possibility. So that's the second one, right? If m is equal to k, that will return 1. No question asked. Now we're going to handle the real scenario. M is larger than k. Okay? Now m is larger than k, which means we have a lot more to choose from, right? A lot more to choose from. So now what we're going to consider, right? Now what we're going to consider is from m, we can choose k, right? From m, we can choose k. From m, we can choose k. Then what? So what's m and what's k? M is 100. K is this. 100, choose 50. I think that should be the 100, choose 50. Jesus, it's a gigantic number. But anyway, so m choose k. Oh, that's not really m choose k. It is m choose k, right? M choose k. Then you order them. Okay, you order them. So m, yeah, 1, 2, 3, all the way to m. It's not really choose k, right? It is choose k. You can just pick k out of it, right? You pick k out of it, but it has to be in this order. So instead of thinking about picking k out of it, we're picking m minus k, right? We're picking m minus k. Now, once we do that, we need to order in such a way that they has to be smaller than what we do, right? So yeah, if we pick out, let's say we pick out k, Yeah, we'll pick out our anchors, right? We pick out our anchors. We have A1, A2, AK. So these are our anchors. They are K anchors. Pick out from this, and they are all sorted. And now we need to fit the remaining into it such that they will always be smaller than, they have to be smaller than both. I just realized, right? It has to be smaller than both. So whatever is putting in between has to be smaller than this, and it has to be smaller than this, right? Because otherwise it just, it doesn't work. Oh, there's also another one. N. N has to be also, yeah, so I think there are more impossible cases. Let's just put them more in there. N smaller than K, right? Or, let's say you have N slots, but you only give me M choices. So if N is larger than M, that's also not possible, right? You need to put more. Oh no, wait, hold on. That is actually possible. I don't think it has anything to do with N because you can repeat. Yeah, it has nothing to do with N. Sorry. It has nothing to do with N. You can repeat. You can repeat your value. So it doesn't really matter. And if you think about it, you can repeat your value. You can repeat your value. That basically means whatever it is, you can just repeat, right? The number of ways. Yeah. Because even if I pick the smallest, okay? I pick the smallest. Yeah, like I have A1 and A2. I need to make sure there are stuff that's smaller than A1 and A2 that I can put it inside. So what is smaller than those two? I mean, it is, I think. Well, hold on a second. What are we saying is we'll pick one combination, okay? One set of numbers. Which was this. Yeah. We choose any set. Let's say we have 3. Okay. Yeah, let's give an example. It'll probably be easier. N equal to, let's say, equal to 5. M equal to 5. K equal to 3. Perfect. All right, so we have 1, 2, 3, 4, 5 to choose from. Okay, then we'll get 3 out. Doesn't matter which 3. 5 choose 3. Will give us 10 different ways to choose. All right. Yeah, we have 10 different ways to choose, and then for each one of them, if we choose 1, 2, 3, we need to find something smaller than 1 and 2. Right? And actually, if you do this, 2 and 1 still works. It still works. It just in between the 2 anchors, it can be anything that's in between the 2 anchors. It'll be fine. Okay, it'll be fine. Then what we need to know is, okay, how many is smaller than that, right? How many is smaller than these 2? How many? Well, I know because that just 2 minus 1 plus 1. That's the number of values in between the 2, right? If you go A and B, The total number in between, just from A to B, is B minus A plus 1. So we know we have two values in between and two values in between this. So now that's just two values, and you can just flip and flop, right? We can flip and flop. How do you flip and flop? You do 2 to the factorial. Flip and flop. And for each one, you can times 2 to the factorial. Should they all be different? Right? That'd be 1. Oh, hold a second. Hold a second. We can have... No, 2... Oh, hold on. Hold on. I think we're getting closer. What we're saying is that we have two values in between, okay? Two in between that we can deal with. Now the question is, where do you put these three? Right? Where do you put these three? There are many ways because we have 5, right? We have 5. I have 1, 2, 3, 4, 5. So we have 5 choose 3 different ways to put them, right? We can put 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. Like there are these many ways to put 1, 2, 3, right? Or these many ways to put 1, 2, 3. Now you have these many ways to put 1, 2, 3, and for each way you put them, let's say we have 1, 2, 3. There's nothing in between here. Okay, there's nothing in between here. So there are 2 more spaces there. Now we need to find how many more values is larger. No, it cannot be larger or equal to. Well, yeah. Wait, hold on. No. This is the last one. So to here, to the left is all 1. To the right is all 3. So if it's 1, 2, 3, that's only 1. This arrangement is only 1. 1, 2, 3, 3, 3. That's it. Now we say, okay, if a 3 put in here, then we have 1 chance here, but here we have 2. So that will be 2. Right? Then we put in here. Then we have 2, 3, right? 2, 3 here. So each one can be 2 choices. So I have 2 choices times 2. I have 2 to the second. Right? This can be 2. This can be 2 or 3. This can be 3. This can be 2 or 3. So that's 4. Right? That's that. Okay. Now I move. Right? Now we're done with this. Now we say 2 is here. 3 is here. Right? So how many is here? That's 2 possibilities. How many is here? Is 1 possibility. So that's 2 times 1. So that's 2 times 1. Now we put in here. That's 2 times 2. Right? So what do you see throughout this? So what do I see throughout this is what do you see throughout this? It's to the powers, right? It's to the power. And depending on k, okay, you will have the number remaining. But it also depends on whether it's to the left or whether it's to the right. Now to the right, it depends also on the anchors. No, it's the same. It's the same. I think as long as you pick out your anchors, okay? Once you pick out your anchors, it's the same. It's the same function once you pick out the anchors, because there's simply no other way. Because no larger than the last anchor, even if you have more choices, you cannot do. Smaller than the first anchor, even if you have, you can now do, because that has to be your first one. Therefore, once you find the anchor, the result is, determined. Misdetermined. I think every anchor, every set of M anchors will give you the same result. Everyone will give you the same result. No question about it. Right? No question about it. So we will have the same result. You will have the same result once you get a set of anchors. When you have the set of anchors, it will give you the same result. So it doesn't really matter which anchor you pick. Now the question, the problem is, what do you do with it? Actually, no. Right? If you look at this, right? If you look at this, hold on. When you pick an anchor, there's something to the left and something to the right, right? That's what the anchor is about. So you just need to split the numbers in between, right? Spread out the number in between. We don't know how many gap, right? We don't know this. We can call this gap 1, gap 2, all the way. This one could be gap 0. This one could be gap k, and this is gap k minus 1. All right, these are the gaps you have. And within each gap, that's going to be A2 minus A1 plus 1. That's the number you can choose for this gap, right? And the gap is just how many is in between. So if it's 2, so that's to gap 1 power times, right? This is going to be A3 minus A2 plus 1. Gap 2 power, all the way multiply to AK minus 1 plus 1, gap K minus 1 power. And then towards the left, okay? Towards the left, there's nothing you can do towards the left. Right? Nothing you can do towards the left. So towards the left is just 1, because it has to be equal to A1, right? And to the right, it has to be smaller than, hold a second. To the left, there's nothing you can do, right? To the left, there's nothing you can do, because we're saying this is the first one. It has to be the first one on the array, because you have something earlier than that, it's not possible. So this is actually not a concern. There's nothing on the left, okay? Nothing on the left, but there could be something on the right. There could be something on the right, as long as it's smaller than AK. So at the end, we need to times. So how many is smaller equal to AK? Well, AK minus 1, right? That's the smallest plus 1. That's AK. We can say AK minus 1 plus 1 times gap K, right? So we have that. What do you think? Now we do have all these gaps. Is there something that you can work out? Well, what we do know, right? We'll have another thing that we do know is gap 1 plus gap 2 all the way plus to gap K shall equal to n minus K. Right? That's what we know. All the gap added together, we know what this value is. But the difference between the two values, that is uncertain. That is uncertain. Can have many different things out there. Right? Can have many different things out there, depending on what the k value is. And I just realized if n equal to k, it's also only 1. Right? N equal to k, then these add together has to be 0. And the only way to add up to 0 is this one become 1. Oh, it's yeah, n is a little bit tough to deal with. So yeah, so I say this is kind of like the formula. But how are you gonna handle this? Right? How are you gonna handle this? It's just the difference between the two. And you can have as many as n, 50. Right? 50. You want to try the n equal to 5, m equal to 5, and k equal to 3? Right? Let's try it. I will just do 1, 2, 3 again. 1, 2, 3. Okay? So with that, we have 3. Okay? So we have g1 plus g2 plus g3 shall equal to 5 minus 3 shall equal to 2. So we have 2 spots. Okay? 2 spots. And there are different ways to get to 2 spots. Right? Different way to get to 2 spots. And the difference is all the same. Right? So we have all the same. So basically, what we're saying is 2 to the g1 power times 2 to the g2 power times 3 to the g3 power. So that's equal to 2 to the g1 times g2 times 3 to the g3. No, this would be plus, right? And that will equal to 2 to the 2 minus g3 times 3 to the g3 power. Okay? Then we can say g3 is, it can be 0. g3 is 0. So we have 4. g3 is 1. That'll be 6. And g3 is 2. That'll be 9. Okay, so we add them together. So give you 19. So one of them give you 19. I have 10 of them. Is that 119? 190. It's very important to make sure this one at least is correct. So my guess on this one, 190, is that correct? That's not correct at all. It's not correct at all. Did you get it wrong? No, 553. Dude. That is not right. And then recheck 5, choose 3. Yeah, it's 10. So we have 10 different ways. And for each way, we know the first one, right? And then we have the gap, right? We have the gap between, because n equal to 5, right? N equal to 5. So 585, that's not what I had hoped. Why is it not right? So we only have two options for other things to go. Ugh. Right, you have a gap between the two. You have a gap, and then in my case, we only have three values, right? We have A1, A2, and A3. A1 has to be at the front. And a gap between this, we call it G1. The gap between this, call it G2. And the gap between this, call it G3. And because I only have 5, so these three add up could only be 2, right? That could only be 2. So, and the number of choices has to be between these two. So if we do 1, 2, 3, there's only 2 choices for this gap, 2 choices for this gap, 3 choices for this gap. That's why I write this, this, and this. Right? You know what? Let's simplify it. Let's do n equal to 3. Okay, m equal to 5. K equal to 3. Okay? So that should be 10. If we do this, that should be 10. Okay? That's correct. Now we just increase it slightly. N equal to 4. Okay? 4. So we have 1, 2, 3. Right, so we have one gap can be on, different. Oh, hold on. No, it's fine, Right? So we have 1, 2, 3. So we have gap 1, gap 2, gap 3 again. I think it's still 2 to the gap 1 times 2 to the gap 2 times 3 to the gap 3. And G1, G2, G3 added together should only be 1, which means it's 2 to the 1 minus G3 times 3 to the G3. But again, G3 can be 0 or 1. So G3 is 0, we get 2. G3 is 1, we get 3. Right? So multiply them together. Wait, do we multiply them together? Do we add them together? I think it's add them together. Oh, I seem to realize what the problem might be. Hold on. But anyway, so if gap 3, yes, this one has the same problem. You can't just do this. You can't just do this. Okay? Because I mean it's good and nice, right? But wait, hold on, you can. Why you cannot? Because the gap is the same. Oh, when the gap becomes not the same, then you cannot do this. Do you realize that? Right? Do you realize that? That's just one of them. Yeah. So it is 5, right? For this one in particular, for 1, 2, 3, it is 5. No question. But, so maybe, so like for 1, 2, 3, 2, 3, 4, and 3, 4, 5. Boom, everybody is 5. So this will produce 15. But you also have 1, 2, 4, right? 1, 2, 4, 2, 3, 5. With these two gap, that's 2. You also have 1, 2, 5. Gap 3. Right? So for this is going to be, again, 2 to the G1 times this is not. This is 3 to the G2. 4 to the G3. So how you can deal with that? Dear God. The gap. But anyway, you can do that, right? 2 to the G1, 3 to the G2, and 4 to the G3. And G1, G2, G3 can be any kind of numbers, okay? Any combination of G1, G2, G3. And I also have 1, 2, 5. And we're not done yet, right? That's just 1, 2. And we also have 1, 3, 4. 2, 4, 5. And then we also have 1, 4, 5. We're missing 1. There's only 9. Which one did I miss? 1, 3, 5. Right? 1, 2, 3, 5. Oh. This we can list them out. Oh, how can you list them all them out? You can't. I mean the pattern. But no matter what, right? No matter what. So we have, these are patterns. Okay. So let's just, write out the pattern. Let's just see if the pattern has something to them. Because I am not sure if there's some pattern to them. So this pattern, so we have, again, G1, G2, G3 is equal to n minus k. In this case, is equal to 1, right? So in this case, the pattern is 2 to the G1 times 2 to the G2 times, Lord, the last one's different, A3 to the G3. Okay. All right, and then we have, oh, write it out. 3. Okay, and then we have different, and then we have 2 to the G1, 2 to the G2, 4 to the G3. And 2 to the G1, 2 to the G2, 5 to the G3. In this case, it's 2 to the G1, 3 to the G2, 4 to the G3. 2 to the G1, 3 to the G2, 5 to the G3. Okay, that's that. So this is the first 3, second 2, this pattern, 2 to the G1, 2, 3, 4, 5, 4 to the G2, 5 to the G3. My lord. This, well, that's 3 to the G1, 2 to the G2, 4 to the G3. 3 to the G1, 2 to the G2, 5 to the G3. This 4 to the G1, 2 to the G2, 5 to the G3. And then this 3 to the G1, 3 to the G2, 5 to the G3. Did you have any pattern for this? And you add all of them together. Right? You add all of them together. And G1, G2, G3 can take different values as well. Wow. I was just trying to say maybe if we add them together, we can find some pattern. And honestly, I don't see any pattern. There's no pattern. Can't see any pattern. Okay, overall, this pattern is pretty weak, but can we at least figure out how many patterns there are in each group? So if we can find out, then we just need to focus on each group, right? Because they are all the same, almost all the same. But there could be, you know, different types. Like you have to find exhaustive all the groups. Well, if you start on the first one, you definitely can find all the groups. Right? Because any group that exists later on, it will have its replication in the first one. So if we just start everybody just close to each other, right? And then we move the last one all the way to the end, done. Then we start to move this. There are too many. There are too many. Man, there are too many. snap out of it. Snap out of it. But let's see if DP can help. How would DP help? Well, DP, let's say if we know NMK, okay? Yeah, it's just when there's no chance of you figuring it out, let's just say if our state is NMK. How would you do it? So M N M K. Okay, we want to calculate this. What if K is equal to 1? Right? What if K is equal to 1? So N is 4, okay? M is 5, but K is 1. What if K is equal to 1? So K equal to 1 is going to be this, 2, 3, 4, 5, so it'll be 5. K equal to 1, answer will be 5, okay? If K is equal to 1, answer is 5. No. No. No, 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 no. Dude, I just realized why it's not. Come on. Come on, that was too weak, man. That was way too weak. Alright. If all ones, that's 1. If it's 2, right, use your same analysis. Same analysis, right? Same analysis. The starting anchor, if it's 2, then we have because you only K is equal to 1, so you have 3 left, right? 3 left. So it's 2 to the third, 3 to the third, and then 4 to the third, and 5 to the third. You add them together, right? That will give you 1 plus 8 plus 27. That doesn't make any sense though. Expected 55. Repeats. We're having a repeating problem. If our first is a 5, wait, what type of repeating problem are you having? If we start with 5, right? 1, 2, 3, 4. If we start with 5, what's this value? I say it can be 1 to 5. He didn't say we cannot repeat. Yeah, we can repeat. So this can be 1 to 5, right? This can be 1 to 5. So this can be 1 to 5, and this can be 1 to 5. This can be 1 to 5, and this can be 1 to 5. No, hold on, I want to have 4. And you're telling me it's not 5 to the third? Bummer. How is this now 5 to the third? Okay, we need to further reduce the complexity. All right, n equal to 3. M equal to 2. 1. K equal to 1. Now that's 1, we know. M equal to 2. Okay, we simplify it. So 3 slots. Okay, m equal to 2 is only 1 and 2. And then k equal to 1, so it will be 1. So that's 1. Or we start with 2. And I would say we have 2 options and 2 options. That will give us 4. So I say this will give us 5. That's 5. Then y 4, 5, 3. I must have putting a different number in there. I have no clue why. Hold on. What value did I put in earlier? I put 3, 5, 1 instead of 4, 5, 1. Okay. But still, okay, 3, 5, 1 is still not right, I think. But 3, 2, 1 is right. Okay. Let's try 3, 3, 1. All right, let's try 3, 3, 1. 3, 3, 1. How would you do 3, 3, 1? So 1 will be 1. And 2 will be still 4. But we have a 3. And if it's a 3, that's 9. So I'll call this 14. 3, 3, 1. Right? Just let's chip at it. 3, 3, 1. Is that 14? That is 14. Okay? That's 14. Now we do 3, 4, 1. Right? 3, 4, 1, everything is the same. We just plus 4 to the... Right, so that will be 30. 3, 4, 1. Yes. Yes. Now 3, 5, 1. Plus 25. 55. That's 55. 3, 5, 1, 55. No problem. All right. It makes perfect sense, right? So how about we say now equal 4? 4, 2, 1. 4, 3, 1. 4, 4, 1. 4, 5, 1. Things like that. Now 4, 2, 1. It's still, but that's just gonna be 1 plus, if you start with 2, then you have 2 to the third. Right, so that will be 9. And this will be 9 plus 3 at the start to the third. Right, that's what? 36. And this will be 36 plus 4 to the third. What's 4 to the third? 64. 64. Is that a 100? All right. 64 is 100. And this plus 5 to the third is 225. So this is not what I'm not sure, because I remember it gave me a different result. It's okay. It's just, run this. Trying to figure out the pattern. We're doing trial and error. I don't even care. 936, 100, 225. That's correct. Okay? So we have solved. We basically have solved, right? N, M, 1. We solved this. NM1 is equal to 1 to the n minus 1 plus 2 to the n minus 1 plus all the way to m to the n minus 1. Done. We got it. We got this. Okay? We got this. This is NM1. Now we need to try to figure out NM2. Okay? How do we do NM2? I mean, we go back down to our favorite. What is our favorite? Our favorite is 3. N is 3. we might as well. What if n is equal to 1? Yeah. What if n is equal to 1? So that's also another thing. Or n is not or. N is smaller than k. Because we have to have at least k. Okay? We have to have at least k. That's just a given. So if n is smaller than k, then it's just not possible. What if n is equal to k? Well, n is equal to k, actually there are many options. So we can't just do that. So how about we start with 2? We know 2, 2, 2. Has to be 3. So it'll be 1, 2, 1, right? So if we'll do 1, 2, 1. So if it's 1, 2, 1, basically it's just 1 to the 0 plus 2 to the 0. That's 2. Yeah. So what's that? Two slots, right? We're gonna do 1, and that's 2, so it has to be 1, 2. But we have different choices. We can say if we choose the first one, and then the second one has to be here's what I think that the things will come. Because we can do 1, 2, 1, 3, or 2, 3. The 3 different options, right? And for each option, there's no more. So this is basically just 3. So shouldn't even bother it. We should do 3, 3, 2. That would be more interesting. So 3 slots. Right? We can pick versus 1. Now we have 2 slots. Right? We have 2 slots. We minus 1. So this is the same problem as n equal to 2, m equal to The same, because I can choose the things I already taken. Right? I can choose the thing that's already taken. So m is still equal to 3. And k is equal to 1. I have one more. So this is what we have solved already. 2, 3, 1. And what's 2, 3, 1? 2, 3, 1 is 2, 3, 1 is, dear me, this is your formula. That's your formula. 1, 2, 3. 1 to the 1 plus 2 to the 1 plus 3 to the 1. That's 2, 3, 1. All right, n minus 1. N is 2 minus 1 all the way to 3. So that's 1 plus 2 plus 3. That's 6. So we say when the 1 is the front, they give you 6. Because this will give you 6. But that's not correct. That's not correct. All right? Because I put 1 at the front. This cannot contain only 1. It has to start with 2. Right? Because if you start with 1, you'll have all 1s, and that's not right. N is equal to 2. M is equal to 3. K is equal to 1. But we actually have a condition that the starting position that we cannot have all 1s. So it's actually only 5 if you think about it. There's only 5. Right? 2, 3, 1 is what we have, but we cannot have this. We can only have this. This is good. This is good. This is good. This is good. And this is good. So you have to minus one of them. So this will give you 5. Okay? Now we can say that's like 1 in the front, 2 at the front. Still, the same thing, right? The same thing, 6, but has to involve 3. Which means these 3 can now go. Only this, this, and this. So that's going to be 3. And 3 at the front. If 3 at the front is that very simple because that's just 3 to the 2, 3 to the 2. We're done. Yeah, because 2 at the front, you have to have 3. That's actually not right. Because 2 at the front all we require is we have a 3. That's not 2, 3, 1 though. That's not 2, 3, 1. Because I can do 1, 3. They will work. But 1, 3 is not included in here, but it will be a viable here. Dear me. Alright. I think it's DP, but I cannot solve it. Let's take a look at the hint. Yep. DP prefix sum. Interesting. Alright. DP, build DP table where ABC is the number of ways you can start building the array, starting from index A, where the search cost is C, and the maximum used integer is b. Dear Lord. Hold on. I have dp. I just ABC. Okay, so dp a b c. Hold on, let me just write it again, just so I can help me understand. We will start building the array from index. I don't like a. Hold on. So index is always I. Okay. So we have an array. So this is I. So starting from this index I, a number of ways you can start building the array, starting from index A with a cost. This is the cost, is C. With maximum, I'll call it M. Oh, I cannot call it M. Dear me, I just call it B. That's fine. I just call it B. The maximum is B. Okay, so start from here with a search cost is C. Okay, and the maximum used integer is B. Maximum used integer is B. Okay. So we start from, and that's fine. We just from an index. So what's the what would be look like? Okay, let's say if I want to find IBC, okay, we start from this index, going all the way to the end, most likely. I want to find the total number of ways to build an array like that, and with the cost, okay, I have a cost, and the maximum integer used. Maximum integer used is B. Okay, I have a maximum used integer. Now, we do know the max used integer because I have M, right? I have M. So now that I have M, I know the question. So to solve the problem is to return dp, right? Start from 0 with max max integer used as M, with a cost is k, plus dp 0 m minus 1 k plus plus dp 0. Well, because we need to have k, right? So the max integer used, the least max integer used is k. Right? That is the solution, the final result. Okay. Maximum use, we have to use m, right? We have to use n minus 1. We have to use k. Okay, so how do you deal with this if you have that? But maximum use, right? Maximum use. This seems to be an easier case to solve. If we start from here, right, and then we say max use, we cannot go beyond that, right? We cannot go beyond that. Max used is B. Okay, I is easy to understand. It's just where we start. B is the max we use, and B has to be larger than C. Larger or equal to C. Because if B is smaller than C, if B is smaller than C, the largest used is smaller than C, and that's not possible, right? That's not possible. So now I have the largest used. And then we say well, cost is C. So cost C means in this stretch, right? In this stretch, we have cost C. So it doesn't really matter, right? I doesn't really matter. It's just going to be a stretch of array. I have the current cost. I know the current cost, okay? I know the current cost. And then I know the max value that I have to use. I have to use it, right? No matter what, I have to use it. Then if I plant this max used value to a certain position, I put it here, okay? Max use, because if I know the max used, I put wherever the max used. The remaining is easy. The remaining is easy. If I put it here, the remaining is just b to the 0. There's only one way, right? I put it here, the remaining is b to the 1, right? So wherever I put the max used, oh, excuse me. Wherever I put the max used, the remaining will be easy. We just the max to the power of that, okay? So that's not an issue. Okay, let's just say we put b somewhere. Okay, we put b somewhere. Let me redo this. If I put b somewhere, okay, then what we need to solve is we need to solve this part, right? Because when b is certain, we don't have to deal with the remaining. Does that make sense? If the largest value, if I have the largest value, I put into a position, right? Because it's the largest value you use. Then to the right of it, it can be anybody. So I want to know in this range, what if we do I and j? Right? So this range we say from I to j with max value used has to be c plus 1 all the way to, wait, hold on. We used 1 already, right? The cost is c, that's c, so the cost is c minus 1, right? C minus 1, which means the max you can use is c minus 1, right? C minus 1, c minus 2. All the way down to what? Because we have to have a cost of c with the max value b that we allowed. And b is larger than c. No, that's b minus 1. B minus 2. Right, b minus 1, we want a c minus 1. C minus 1, all the way to c minus 1, c minus 1. Is that right? Because we put a b value, now we have from I to j. Right? So from I to j, we want to know is given, because I already find one cost. So the remaining should have c minus 1 cost. Right? Remaining is c minus 1 cost. And with c minus 1 cost, the largest value I can use is b minus 1 or b minus 2 all the way to c minus 1. But that's slightly different from what they're saying. They're saying it's a 3 level, mine is like a 4 level. Right? Dude, it's a 4 level. 4 level. That is a 4 level DP. So indeed, it's a 4 level DP. I mean, if you do caching, it probably won't matter that much. Ah, yeah, we don't have to because... No, yeah, we have to. And the j has a cannot be smaller than a certain value because c minus 1, right? It had to have at least c minus 1. So from c minus for a range all the way to c minus 1, right? We have that plus 1, so to c minus 1 with the largest value is b minus 1. And that's only one possibility because n is equal to the cost. Right? N is equal to the cost. That's only one. That's actually not true. That is not true. Because n is equal to k. That's not true. N is equal to k does not signify anything. N is equal to k does not signify anything. Right? That's not what we want. But when n is equal to k, we know it's n is equal to k. N is equal to k. And we know who's the biggest. Oh. You just have to keep going down, right? N is equal to k. It's the same thing. You can put if n is equal to k, right? Now k is the largest. No, k is not the largest. And you have k is the number of cost, so everything, so it has to be sorted, right? Sorted going up, and you know the largest one, right? And then we can say, okay, I know where I put the largest one. That's basically saying you know where you put the largest one. Then you can have the second largest one has to be in front of you. Then you can decide what that second largest one can be. Yeah, basically just like how many different positions you can put the largest one. So you can put the largest one. Second largest one has to be b minus 1, right? b minus 1. You can say, and this is b minus 1 is the largest, or b minus 2 is the largest. Yeah? But doing 4 levels probably is not going to work. Let's try to see. I have another hint. Doesn't really help. I haven't figured out how to do 3. I haven't figured it out yet. all I figured out is put in different b's. Does it matter? Does it matter if I put B here, right? Does it matter? All we want is for the same one, right? If I want to find a IBC, okay? I want to find an IBC, right? IBC. That's what I want to find at the current moment. We say to find IBC with max value B and then the cost is C is equivalent to find C minus 1 with B minus 1 is the largest. Right? If I can find starting from I with B minus 1 is the largest. Right? I have starting from I with B minus 1 is the largest. And then we will record C minus 1 cost. Right? We have the total cost with B minus 1 as its B minus 1 as its largest value. And then we, for each one of them, can I say I just put B somewhere? Oh, you definitely cannot put in the front. Right? You have to put B. What if B minus 1 is at the end? So you have to find all of them with B minus 1 is not at the end. Right? B minus 1 is not at the end. See, that's where I don't understand. B minus 1 is not at the end. That's why I do I and J. I think with I and J it's clearer, right? If we do I and J. But I just have fear, right? If I do I and J, that's gonna be a 4D DP. I don't think that's gonna be right. But with 3D DP, I just couldn't. I could not figure out the transition. I'm gonna think again. So starting from I, right, we say, starting building an array, starting from an index, where the search cost, I know the search cost, I know the maximum used integer, right, I know that. So if you know the maximum used integer, and you want to break the problem down, and so I say, like, what I can think is, where you put, right? Where you put the maximum used integer. I put the maximum use integer at different positions. And you just go back. You go back to the IJ idea, the 2 pointers idea. I don't think that's the way to go. Or maybe by doing that you can figure out. I don't know. It's way too long. Let's take a look at the solution. Couldn't solve it. I just want to know the intuition. Yeah, I'm not using Java for this. I spent way too much time on this. I need to know. What the heck? Hold on. Max so far. Remain. What's this remain? How many arrays of length n with values in the range exist such that you will find exactly k new maximum when traversing? Exactly. Right? We have understood that. Given the maximum number of possibilities, massive, right? Of course, you cannot build it. How many elements have we placed so far? Suppose we add elements to the array in order. We can represent this with an index I that indicates the index of the next element of a place. For example, if the current array is this, the next element we will place is at I equals to 3. Correct. The maximum element in the array, we can represent this as a max so far. Max so far is 6. How many remaining new that's different. That's different from the hint. How many remaining new maximums must we encounter before the end? I can represent this as a remain. Example, both 1 and 6 are maximums. So, okay, so this is different. Okay, this is different from the hint. Okay, this is different from the hint. This is saying max so far. That's very different. And remaining, none of remaining maximum that we need. Right, so this is, the DP is based on this, which is saying, if you're starting from I, right, again, you give an array, you're starting from I, we know the max so far. Wait, hold on, what's max so far? So the maximum has used so far. The max that has been used so far. That is important information. So the max used so far. Okay. And the remaining maximum. We have the remaining maximum. So we want to find out how many ways to build. Okay, so we start from I. Let's say we know one max has been used so far, and then we have the remaining max. Remaining max, new maximum, remaining new maximum, the thing that we haven't used so far. That is not really helpful. That's actually fine. The remaining max has to be larger than the max so far, right? Yeah, it's understandable. So what basically the max so far, okay, I get it. They have the max so far, and then how many more How many more maximum do you need, right? How many more max do you need? And the solution to the question will be, you know, we start from 0. Max so far is 0, right? Because we didn't do anything. And the remaining is going to be k. 0, 0, k. That's when we start, okay? So now what we have the max so far, we know, which means we have to give bigger, right? We have to give bigger. And we have the number of remaining to put, right? So we have the number of remaining to put. And we actually know what those values are going to be. So there can be the max so far, right? Max so far plus 1 all the way to m. These are what we can choose from for the max and remaining. And we can say for the max remaining, and it has to be sorted, right? It has to be sorted. So we can say max so far plus 1 all the way to m. We choose. So we choose the first one, okay? No. Because we want to say from this towards the end, how many, right? How many? Okay, so we say, all right, if I put the next value in here, right? I put max so far plus 1 in here in the I position, and the question will be, it will equal to, right? So hold on, let me do one more time. If I is here, right, and we say the next current max, right? Current required. Okay, the current required. So if we put the current required here, then the problem will be dp I plus 1, starting from here. Current required is c plus 1. And the number remaining will be r minus 1. Because we used 1, right? Or I can put the current here. If I put current here, okay? Yeah, current is going to be the current is the smallest maximum that we need at the moment. Then that means we'll have whatever between the previous one. So we know the previous maximum, right? We know the previous maximum is c minus 1. So in this case, that is going to be c minus that's why you use the max so far. Okay, max so far. Previous max. So we took pre. Okay. So we have I pre and then remain. I pre R. IPR. What's IPR? IPR. Okay. So we have the previous max. So currently we can put the current max at the front, right? If I put the current max at the front, so that's just going to be p plus 1. That's my current max, right? Or I can put current max here. So that's going to be dp. So I going to be here, right? I plus 2 p plus 1, I minus 1. So I start from here. Previous max is p plus 1, and I have the remaining. But because I'm putting here, so that's going to be p plus 1 is the current, minus p, right, plus 1. So that's going to be 2. So that's going to be 2 possibles we can put in between. So 2 to the 1, because we have 1 position, right? Again, we can do dp I plus 3. So I plus 1 plus 2. We will start from here, right? We start from here. If we start from here, no, we put the current max at this position. Then when we start from here, and it's still p plus 1, because that's what we add when we put it here, and then r minus 1. So if we put the current max here, then we have 2 position open. So that will be 2 to the second. Right? We go all the way down. But that's only one possibility. Right? We can also do the current. We can do p plus 2. There's no... Right? We can do p plus 2. We can put it here. Put it here, put it here. Put it to p plus 3, p plus 4, p plus 5. Doesn't matter. Right? Doesn't matter. And then all the way to the end. See, that might be... I want to give it a shot. I've been doing this for so long. It's time to put everything into test. I am not doing this with Java. I can guarantee that. Screw this. We even Python this. Spent way too long on this one. Oopsie doozy. That is Java. Alright. So, what do you think? We need to find the not this one. We need to find the edge case. Previous max and the remaining. Right? That's what you're trying to define. Def dp I pre-max and remaining. dp remains the most important and the most difficult. I mean, both dp and graph, they're both difficult, but graph is difficult because you don't know the algorithm. Somebody in the past has already figured out. dp is difficult because it's an IQ test. That's basically how it is. Okay, anyway, so r is the number remaining, okay? R is the number remaining. Let's just say r is equal to 0, right? We're starting from I. We have a previous, okay? We have a previous. And then we want to decide r is 0. What does r equal to 0 means? So we don't have to have anything. Wow. Hold a second. Let's get a mod. Right. R is basically, r is 0. If r is equal to 0, doesn't really matter what p is, right? We don't care. We just p is the previous max, and then r is 0. Then that just means everybody p or smaller. So it's p. Power. I remember pow has p raised to the power. Yeah, I remember this. Python pow. Mod, right? So we start from I, so we don't know how many left. So it'd be n minus I, right? N minus I is the number of position left, and then they can all be modded. We just return this, right? If r is equal to 0, we just take the current, the previous largest as the largest we can get, and then every position can be that many different choices. Doesn't matter. Okay, so that's r equal to 0. Other than that, we can start thinking what the current max can be. Now, p plus 1, p plus 2, and of course, we have a limit on p, right? The limit on p is if p exceeds m. I mean, we can make sure p does not exceed m. We should. Basically, we say if p goes beyond m, right? If p is larger than m, now hold a second. P is the previous max. So if the previous max is equal to m, I was thinking about equal to m. If the previous max is equal to m, because it does not start, right? If the previous max is equal to m, what's going to happen? Then we cannot have any more, right? So if r is this and p is smaller or equal to m, if r is not equal to 0 and p is equal to m, that is 0. Right? The previous max already taken on the max, so I cannot have any more to give. But if it's still r, then that's it. Nothing. Okay, makes sense. Makes sense to me. What else? Now the remaining is r is not equal to 0. Why you do p smaller or equal to m? Because if a p larger than m is not possible. But p larger than m, no matter what, is not possible. So we probably should do if p is larger than m. I'll just read 0. Alright, then we can just say p is always going to be smaller than equal to m. Right? P will always be smaller or equal to m. And when r is 0, we do that. Right? And if r is 0 and p is equal to m, that's not good. Or we can just say or p r is not, or r and p equal to m. This is going to be 0. Alright, p larger than m, no. It's an impossible case, right? Or p is equal to m, but we still have more r to give, not possible. Now r equal to 0. So now is r is not equal to 0, so we have more to give, and p is smaller than m. Smaller or equal to m. Right? P has to be smaller than m. Because if p is equal to m, it's either r or r equal to 0. So yeah, okay. So this is p smaller than m and r is larger than 0. So in that case, right, I have the next one to give. So I can go through p, right? So for current p, Okay, can be in range. We can do the same as previously. Can we do the same as previously? No, we cannot. I don't think so. I don't think we can. It has to be bigger than previous. Because if we're the same, that will be handled by a different I. So it has to be plus 1 all the way to m. Right? All the way to m. This is the current p. What current p can do is that. And for each p, right? For each current p, we can put them in different places. Right? We can put them in different places. You can put them on I. Right? When we say for j in range, I towards, now that is an interesting thing to do. Towards what? Well, if we want to make it easier, let's just say towards the end, right? But then we have to do one more check on I and n. Because I have r remaining, so between I and the end, there has to be at least r. If there's not enough r, which means if we don't have enough, right? What do you mean we don't have enough? We probably can avoid doing that and make some, don't go all the way. So we have r to give, right? Start from the current. We have r to give. So that should be n minus r. N minus r. So n minus 1, minus 2, right? If we have 2 remaining, right? If we have 2 remaining, then 2 remaining positions that we have to have the current largest. If we have 2 remaining positions, then the current one, now this j is the next one, right? The j is the next one. No, j is the current one. Where do we put the current one? Right? So the j, where do we put the current component? Here, the component here, 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 and to n minus r. J can be put in n minus r. If r is equal to 1, j can be on 1. So I think it should be plus 1. Right? And then we say, for each position that I'm going to place, we're going to do dp, right? So j is where I'm going to place the current p, okay? That's where we're going to place the current p. We're going to place the current p at the j position. So the start should be j plus 1, right? The start shall be j plus 1. All right, j plus 1 to be current p is the previous max, and remaining, which is r minus 1. That's the remaining. Or there's not enough position to get r. That's not possible because I already handled this j. We'll make sure there's always enough room left. There's always enough room left. I don't think this is M. I think this is R. Now this is M. P is the max. R is the number of remaining. R determines the positions, the spots, the number of spots remaining. And by doing this, I already guarantee there'll always be R spot remaining. Right? So this plus, I'm at J. Okay? I'm at J. And then we can say J minus I plus 1 is the number of spots in between. Right? Number of spots in between. Actually, it should be like this. Minus 1. The number of actual spot in between I, so J. Right? If it's 0, 1, 2. So it'll be 2 minus 0, so it'll be like 2 in between. Right? It'll be 0 in between, 1 in between. So all these can be any value. These shall be power to that, right? Mod equal to mod. So what is this power raised to the power? So that's just the number of options we have. It should be current P minus P, right? Plus 1. That's the total difference we have. So if the previous P is 1, current P is 3. We have 3 minus 1 plus 1. We have 3 value to put in between the gap. So that is the gap. Right? So we can say, when the rest. So if the rest equal to rest plus and this whole thing mod, and we'll return rest. So the final will be what? So dp we start from 0, right? With previous max is 0, and remaining is k, or k remaining. Or previous max can be 1. Or previous max can be 2, 3, 4, 5, doesn't matter. So the previous max, right? Previous max. Right? Previous max can be 0, can be 1, can be 2, all the way to a certain point where you cannot go more. Yeah, if the previous max is 1, that means you start from 2. Right? You start from 2 and you have to give me k. You still have to give me k. So it depends on how much leeway I have, right? How much leeway I have. So I think this should be m minus k, right? If m is equal to k, then it don't give you anything. Can't give you anything. But if m is equal to k, shouldn't I give you 1? Yeah, so maybe we should plus 1. If we plus 1, then we start p as 0. right? So if P is 0, and M is equal to K. I don't see K again. Huh? Yeah, there's a special case I didn't consider. It shall be how many remaining? So it shall be the previous as P, right? So hold on. That's definitely. And that's fine. I should have another one. Let's say M minus P, right? Is the total number of values still available. If that is equal to K, equal to R, what does that mean? That means the number remaining, the number of available is equal to the number. That doesn't mean anything, right? That doesn't mean anything. Because like if M equal to 2 and K equal to 2, M equal to 2 have only 1, 2. K equal to 2, we at least have to have 1, 2. But then that still can be many different ways, depending on the N. Maybe this is not really the case. Because if I can use 2, if M is 2 and K is equal to 2, right, is 1, 2, but we can put 1, 2 anywhere. Previous max 0, 1, 2, all the way until M minus K plus 1. M minus K. That's the minimum previous that we need to have, which means the current, we need to make sure at least we have K remaining, right? So basically we say P, the largest P we can take is M minus K. So we have M minus K plus 1 all the way to M. So that will have a K in them. Then we'll return rest. Very shaky. Very tricky. Not even sure if it's correct. Nope. That's way out of the range. Nah, it's not right. I can't even get the first one right. 4, 2, 1. That is bonkers. I start from I. Yeah, because when I have 2. No, n is 4. That's 4. So we start from 0. Previous is 0. And we have 1 remaining. Okay? Okay, so put it in. There's 0 and a 0. So don't do this. So is r equal to 0? R is not a 0. IP is 0. R is 1. P is 0. So from 1 to... So we say we can do 102. Right, 102. So if we say current P is 1, and for J in range, this R. That's not really helpful. Okay, R is 1, and N is 4. Yeah, this we have, no, that's not right. Because we put it on all those positions. That should be the first one, okay? That, when you put J, that should be the first time this value occurs. So everybody in between should be the smaller ones, right? Everybody should be the smaller ones, which means this power, I fear the power should be the ones in between, which means should be minus, right? If we go 2, 3, if we do 2, 3, then there should be nothing in between. Then if you do it this way, then it depends on, so this J, it cannot just go like that. It depends on how big the current P is, right? So what I'm saying is, try this. I'll go down to 40. Still not right. So current is 1 and J is equal to 0. So J is here. Current P I want to put 1 in it. Then J equal to 0. Then we call next one is J plus 1. R minus 1. What is R? R is 1, so 0. That should return 1. Why did it return 2? I think this will return 1. Current P is 1, right? P is 0, so 1 minus 0 is 1. That should be 0. That should be 0. That should be 1. Interesting. How is 0 to the 0? 0 to the 0 defined as 1, dude. So what are you gonna do? Oh, I don't think this is plus. I think this is minus multiply. Well, still not right, but I think it'll get a little bit better. It should be multiply, right? What we have here on the left multiplied by what we have on the right. I think so far so good. I think the problem is that is also right. Problem is this. Current is 2. J is 1. Okay. So current and J is 1. So 0, 1. J is here. 2 is here. Okay. Then we say this is 1. This one only have 1. 2 minus 0 minus 1, 1. So that's a 1. Just doesn't care. Next res. Next res is dp. dp2. So from here, current is 2, 0. R is equal to 0. And now I go here, R is 0, right? P is 2. P is 2. What is this? This is starting from this position. With previous max is that. Previous max. I have a previous max. And here. It has to be. Then I basically say we have can do 1, 2, 1, 2. Oh, that's duplicate from the previous situation. Ugh. We have 1 power already. What do you think? We already have a power situation. We have a power here. We have a power here. Right? Yeah, we put a 2 here, we got all the power here. We put a 2 here. Now we duplicate the situation. Yeah, we duplicate the situation. What if I say this is p minus 1 and we do this. Alright, screw this. I don't know. Yeah, we know that. Yes. Oh, hold a second. 0, 0, k. You don't have to add them all together. Well, I think no matter what, even if you do that, I think it's still wrong. Previous max with that remaining. With previous max with that remaining. And we have the current max. We can put the current max at all these different positions. And in each position, right, the current max we're putting here. N minus I. Maybe this should be minus or minus 1. That's not right. If I is equal to n, which means we have filled everything. If r is equal to 0, that's 1. If not, that's 0. Otherwise, it has to be n minus I, because I cannot do power on this I position. It has to be I plus 1. And then we'll just go through n minus r. R is remaining, right? N minus r, then plus 1. Five, 3, 3. No, 5, 4, 3. Yeah, still not right. Maybe this? Nope. This doesn't make any sense, huh? We start on 0, previous is 0, and now have k, right? So we're starting from a position. Previous is some other max, and we have r remaining. Now we say the current one can be of these values. Current can be these values. Yeah, it's just to waste too much time. We got that. Okay. Okay, so the base case that they have is if r is smaller than 0, return 0. Replace a number that is not a new maximum. Oh, that's a very different way of thinking. After we place this number, the next state holy crap, that is correct. We have these new ways. Oh, here, I think it's hard to say like what was the problem. I think the problem is you're trying to mathematics it at the same time also trying to DP it. So option 1, the current value is the same as previous max, is not as big, is no bigger than previous max. Equal to previous max times dp I plus 1 period max r. Option 2, the current value is one of the is bigger than previous max. Then for current in range, because it has to be bigger, but it cannot be more than m. Right, as the current one. And then we'll do the same. Nope. It's bigger than the previous max. Current is bigger. So current is current, right? It's bigger than the previous max. And if it's bigger, we will accumulate a 1. It's not right. Oh, shoot. I can take M. Oh. Yeah, I'm not gonna do the space. Oh, there's another one. Prefix sum. You gotta be kidding me. Oof. All right, I think there's one more to deal with. A different DP plus prefix sum. We probably have to deal with this. I'm not gonna just let this slide. But yeah, that's it. This is a nightmare. Sure. Okay, so we have to summarize. Okay, initially try to math it, but didn't work. So pretty clear it is DP. Yet I was not able to find the correct state for DP. The solution, right, is a fail. The official solution defines the DP as DP index previous max used remaining max to use. Then for transition, we think like this. What is the options for the current, right? For the current index, it can either be a previous max, right? It can either be a previous, it can be any value no bigger than the previous max, or it can be one of the new max. Then done. That's it. That is it. Yeah, M and K, right? But we did this here, so that's M squared. Oh, that was a big fail. I was actually glad that I didn't do it yesterday, because it's gonna really drop me into depression zone. Alright, that will be it. I'll see you guys again in a couple hours.